Buenas tardes a todos, muchas gracias por venir. Tenemos nuestro coloquio IIMAS con la invitada especial, la doctora Jocelin Lega, que viene de la Universidad de Arizona. Ella es profesora de matemáticas en la Universidad de Arizona. Copié una poquita de información de su página de internet, que es una muy buena página, por cierto, el diseño está fenomenal. Y apunté unas poquitas cosas, ¿no? Ha sido directora del programa G-Teams, que es un programa muy interesante de colaboración entre alumnos de posgrado, profesores, para asesorar alumnos de bachillerato. Fue la directora del Instituto para Matemáticas y la Educación, fue la directora del programa de licenciatura de Ciencia Integrada, es tutora activa del posgrado en Matemáticas Aplicadas de la Universidad de Arizona, editora en jefe del Journal Física D, Non-Linear Phenomena, fellow del Instituto de Física de Estados Unidos, editora asociada del Journal Non-Linearity, tiene 59 artículos arbitrados indizados, incluyendo 3 revisiones del estado del arte. Es muy activa en docencia y muy activa en el servicio a la profesión. El título de su plática ya lo tenemos aquí. Three mathematical models, yo le agregaría mathematical, to help understand the spread of mosquito-borne diseases. Thanks very much, Dr. Lega.
Thank you very much and for the invitation to present, and thank you all for being here. So about 3 years ago, a colleague of mine in the College of Public Health, Heidi Brown, she's an epidemiologist, and she got in touch with me to see if we could do some mathematical modeling for the problems she was interested in. And that's what started our collaboration. Her interest is on the diseases that are transmitted by mosquitoes, and I was trying to find an illustration of what it means to have mosquito-borne diseases. So this is from the Center for Disease Control and Prevention, thank you. And so the idea is that you have a sick person who's bitten by a mosquito, then the mosquito becomes infected and bites a healthy person who then becomes infected, right? So it's fairly simple. But clearly you need mosquitoes and a lot of them for the disease to be transmitted. So what I'd like to do today is discuss 3 models that we have worked on that illustrate that come from problems in mosquito-borne diseases. So the first one, I'll start with mosquitoes, right? Because obviously we need mosquitoes to study mosquito-borne diseases. And this is just a model that predicts abundance. Then we'll talk about disease incidence, which is how many new cases of a given disease you have per day, and whether or not you can predict that. And then finally, this is more preliminary than the other 2, but I'll discuss a model that we're looking at right now for transmission due to how people move from one place to another. Okay, and then at the end, I'll put it up together. My goal really is to show that with a collection of small models, we can maybe build a whole program to describe the spread of mosquito-borne disease. So I'll start with the life cycle of a mosquito. So mosquito life starts as an egg, and eggs are laid in water. So the female mosquito needs water to lay its eggs. And then they develop, they have 4 instar phases plus 1 pupal stage. They develop in water. And at the end of the pupal stage, they emerge as an adult. Okay, and then if the adult is a female, they can go through the reproductive cycle, and then after a while just lay more eggs, and it goes on like this. So what's interesting is that the time it takes for an egg to develop to get to the first instar stage, and then for a mosquito which is in the first instar stage to go to the second instar stage, all that depends on temperature. And so I'm going to show you a picture here. So this is in Puerto Rico. That's over here you have temperature, so that's the mean temperature. It's about 26, 27 Celsius. And these are days of the year, so you have about 100 days here. And you see that at the beginning, like, the temperature is above average, and then towards the end it's below average. Okay, so now imagine that you pick a day here. So let's say we pick this day, and then an egg is laid on that day. Well, the color tells you that it will take about 4 days to go from the egg stage to the instar 1 stage. And then from the instar 1 stage to the instar 2 stage, etc. So you follow the line here, and then an egg laid on that day will become an adult on day 16, maybe. Okay. Now, you see that when the temperature is warmer than average, it takes much less time than when it's colder than average, right? I mean, here it would take about like maybe 18 days, whereas here it's about like less 13 maybe. Okay, so and of course how long it takes for the mosquitoes to develop is going to affect how many mosquitoes you have, right? So that's what we want to put into the model, and the model itself just follows each egg. So you can imagine you put an egg in a computer, and then you follow its life, right? And then at any time you can count how many stages, mosquitoes in a given stage you might have. Okay. Now, so we have temperature, and as I just explained, temperature is going to affect the rate or the time it takes to go from egg to instar 1, instar 2, etc. And for any egg to emerge as an adult. Once the adult, if it is a female, then it's going to go through the reproductive cycle and going to need to get blood to sort of be able to lay the eggs. And so that itself, the length of the reproductive cycle also depends on temperature. Right? So that's another place where temperature is being used. And of course, then once the eggs are laid, they go back into here, and then they go through their life cycle again. Now, if it rains, I told you like you need water for eggs to and immatures to sort of develop, and so you need to. If you have no rain, there's no water outside. I mean, unless people have flower pots and things like this. And so if there's no rain, so we take into account how much rain there is and other water sources to sort of describe how many eggs you might have. And then the last piece is that, yeah, I can wait a little bit. So the last piece is that at every day, it's possible for those eggs or those immatures or the adult mosquitoes to die, right? And how the likelihood for them to die is going to also depend on the environment. So it's going to depend on temperature, and it might depend on relative humidity as well. So that's also part of the model. That's the mortality rates depend on temperature and relative humidity. Yeah. So essentially what you do is that we use measurements that were done in the lab with incubators and things like this. So we didn't do that. That we found in the literature to get all the parameters and the development rates for the mosquitoes, the length of the reproductive cycle, that's the gonotrophic cycles, and we also use temperature and precipitation data from weather stations that you have in given locations. If you want to, for instance, be interested in whether or not a mosquito is infected, you need to put into the model how likely it is that if a mosquito bites a person who's infected, they would be infected itself, right? So that's called vector competence. And in the model, the results I'm going to show you, we put it at a constant value, which is 79. And then the EIP here is essentially the time it takes for the virus to develop inside the mosquito. And so a mosquito might bite a person but not become infective until this period, the EIP is over. And the length of the EIP also depends on temperature. So if you want to count how many infected mosquitoes you have, you need to put that into the model. So this idea of modeling things like that came out of this paper by Corey Morin and Andrew Comrie back in 2010. And then since then, we've added a few things to it, and we've adapted it to other species. So this is from our 2015 results. And this is for a mosquito which is called Culex dorsalis. It's a mosquito that carries West Nile. And what you have here is a plot of temperature in Fort Collins, in Colorado, over 9 years. And so you see, well, that's the summer, right? Winter, summer, etc. And in the winter, it can get really cold to minus 15 Celsius. In the summer, it goes up to 20, 25 Celsius. And so if we feed this temperature information into the model, this is what the model predicts. So it predicts that during the winter, there are no mosquitoes. The little wiggles here is because we have a thing that sort of reinitialized the model just in case if it crashes, we just put more mosquitoes in, and if they don't survive, they crash again. So anything that's really like very small is irrelevant. It's just a technicality. So essentially what you see is that the abundance of mosquitoes is following temperature. And so what we did next is that we have a colleague in Puerto Rico who's doing vector control. He's at the CDC. And he had data. He has surveillance traps that he puts in people's backyards and various places. And he had all of the data about those traps. So what we wanted to do is to ask, well, does this model work for a different species, which is Aedes aegypti? And Aedes aegypti, that's the mosquito that carries diseases like dengue and chikungunya and Zika. Okay, and so same story. We had weather stations, so we take the data from the weather station, feed it into the model, and make a prediction. And the prediction is what you see in red here, as a function of weeks in that case. So it's about 3 years, right? And the blue is his data, right? And so that's really bad, right? So we ask ourselves, well, okay, well, what's going on, right? What is special about this species that we do not have in the model? And I never met him, but we had phone conversations, and he had done some work before where he noticed that there was a correlation between rainfall and lots of mosquitoes. So 2 weeks after rainfall, typically there were lots of mosquitoes in the area. So what we said is, okay, well, maybe we need to take into account the fact that for this particular species, which is not true, I believe, for the other mosquitoes, the eggs don't desiccate as well. So if they don't hatch, they can stay there dormant, and then when it rains, they can hatch again. So what we did is that we say, okay, well, we know they resist desiccation, and what we're going to do is that we're going to assume that when it rains a lot, that creates new habitat. And so the eggs can now hatch, and the mosquitoes can sort of develop. The other thing is that after rainfall, especially if it's intense rainfall, the humidity changes, and it's known that adult survival might be affected by humidity, so we also put that into the model. And when we do this is what we get, right? So now the prediction of the model is in black, and then the blue is the data. Right? And you can see that's much better than before, but it's also quite good, right? So we were very happy about this. Now over here, this was one of the areas where he did some interventions. So on that day, it started spraying and then put control traps to reduce the level of mosquitoes. And so what you can see is that after that day, the reduced level, the level of mosquitoes, the abundance is much less. But what the model doesn't know anything about spraying, so the model continues to predict what would have been, how many mosquitoes you would have had if you had not had the intervention. And so I'm going to show you, so then what we did is that we had those parameters for the model, and then we applied it without changing anything. The only input that changes is the information from the weather stations. We inputted that, we ran the model in other locations. So this is in a place called Arboleda. And again, you see that once the model gets going, it picks up reasonably well the fluctuations in abundance. And I have a third example, which is in Playa. So in that case, we had the weather data ahead of time. And so we started running the model essentially about a year and a half before we had the data information. But you can see that again, it's sort of the model picks up the fluctuations reasonably well in abundance. And this, I think, is significant because typically when you have a lot of models that like that involve a population, it's quite possible that over time you get a drift, right? So things accumulate differently in the model, and you can get periods of abundance slightly out of phase. But what was nice about it is that at least if you start a year and a half earlier, you don't get any drift. Right? So we were quite pleased with this. All right, so this is the summary for this first part, is that the new version, the one that includes the new habitat plus the survival of adults that depends on relative humidity, this new part shows good agreement with surveillance trap data. As I said, it used temperature-dependent development and survival rates. And the tunable parameters that we have that are additional are the ones that describe the hatching of eggs after rainfall and also the sensitivity to relative humidity of adults. And so my colleague a while back, we did a sensitivity analysis for the old version of the model. And essentially what came out of this study is that it doesn't really matter the functional shape of the development rate. What really matters are the thresholds. So when the mosquitoes develop, in what temperature range they develop. So essentially that's good because it can allow a lot of model simplifications, because you could, for instance, replace complicated temperature-dependent growth by sort of constant function or linear functions, but the thresholds really are the most important. And then I have a grad student who's doing a sensitivity analysis for those new parameters here. Now, how can you use this, right? Once you have a model, I mean, obviously you have to be able to trust it, but one thing we can do is use it for to measure the efficacy of vector control. Because, for instance, in this case, here the model is predicting you might have like 14 mosquitoes per trap week, but you only measured like 3 or 4, right? And so this is average over many traps. So essentially, you can take the ratio of this to that, and it gives you a measure of the efficacy of your vector control. And so if we calculated this, and it came up to about 80% efficacy, and this is what they had predicted their vector control method was based on other data that they had. So it's very consistent with what they knew already. Now, what is nice is that if you trust the model, you can take that into another place where you don't have any vector control or you don't have any surveillance, and it's going to tell you where you can see the mosquitoes, right? When it is that you're going to have more mosquitoes or less mosquitoes or no mosquitoes at all based on the climate. And it can also tell you where to put your vector control interventions, right, if you're concerned about the level of mosquitoes. The other thing which I think is important is that on this machine, which is a small tablet, the codes I showed you, each one runs in less than a minute, right? I mean, so you can, with 3 years of data. So you could imagine that if you get 3 years of weather data, you run that on your laptop and you get immediate feedback on where the mosquito level could be. You can also put predictions, climate predictions into the model, and then use that as a way to predict abundance in the next years or things like this. Now, of course, that's what I said before. You would like to be able to use it in places where you don't have enough information. And what we're trying to do now is to make sure that we can test the model in as many situations as possible. So we're looking for additional data to test the robustness. And of course, if you have any data that you want to share, please let me know. Okay, so that's that first part. Now I'm going to move to a simple model to describe disease incidence. And so again, incidence is the number of cases reported to the health services when you have an outbreak. So I will be talking about, as an example, of chikungunya in the Americas. And I have a little movie here, so let me tell you what it does. So here you have the date. So it starts in January 3rd, 2014. And you had chikungunya here. It started in Saint Martin in the Caribbean in 2013. So in 2014, it arrived here, right? And then you're going to see those dots. The size of the dots essentially tells you how many cases there were. And if you want to keep an eye here, you can see that in Mexico it arrived fairly late. And so I'm going to run this, and you can see the spread of chikungunya. And this was, so chikungunya was kind of new to this area when it started, and it spread extremely fast. And by the end of January 2015, you had 42 countries or territories that had chikungunya, and more than 1 million of suspected cases. So that was absolutely huge. And you can see, right, you saw how it spread, and it's just like, the dots are really, really very big. So DARPA, which is the Defense Advanced Research Projects Agency of the US, they ran a competition. They said, in August 2014, they say, well, chikungunya is spreading. What we're going to do is we're going to run a contest and ask people to make predictions until, I think it was February 2015. And then we made predictions every week. Once a week, there was a prediction for all of the countries that belong to the Pan American Health Organization. We were predicting the number of reported cases, the cumulative number of cases they will have had since the beginning. And at the end of the contest, they took the real data and they compared that to the predictions, and they scored it, and they ranked everyone. Okay, and we ended up winning the competition. And you'll see that the model that we use is extremely simple. So what I want to advocate for simplicity sometimes, and I'm going to show you what we did. Okay, so typically when you have, so this is for chikungunya in Guadeloupe. Typically the data that you get from health services, or the data we got from PAHO, was something like this. So as a function of time, in weeks, you get reports of incidents, which is the number of new cases. And typically people look at a curve like this. It's noisy, right? It goes up and down. I mean, it could be that this was like Christmas or something like this, where people didn't want to go. They went to the doctor before because they felt sick, and not during that week, and then they went after. So you get a dip and then a big peak. And if you look at the total number of cases as a function of time, you add up all of those pieces and you get a curve like this. And the red line here is just connecting the dots. So obviously what we want to do is draw a curve through this, which is much smoother than just connecting the dots. Right? So this picture here, this is the same as before, but the red curve here is a smooth and interpolated version of what we had before, right? So it just goes through the dots. And once I have that, I can calculate, so this is the cumulative number of cases. Incidence is going to be the derivative, right? So by how much this number changes every week. So I take this and I put on the horizontal axis C, the number of cases, and on the vertical axis, incidence. So this is new. I don't think anyone had looked at the epidemiological data this way, but when you look at it, this is what you get. You get the blue curve like that. And that was for Guadeloupe. The epidemic, when we started, was already over. So I wasn't quite sure what to put in the model, right? I mean, what kind of model we were going to do. But once I saw this, I thought, well, okay, maybe I can approximate this by an inverted parabola, right? If that's the way this curve looks like, well, a one-home thing, which is a parabola, might work very well. And so if you do this, then you realize that what you're actually doing is writing a differential equation where the rate of change of the total number of cases is the formula here for an inverted parabola. And this formula has two parameters. One is m, the maximum of the parabola, which is here. And then the other one is where the parabola crosses the horizontal axis. It's going to cross at 0 and it's going to cross somewhere else. That's what I call C naught. And so you can write something like this here. But this equation is very well known. This is the logistic differential equation, right? So all of a sudden we're modeling diseases with the logistic differential equation. And so that gives you a prescription to our method, if you want, to model. So I'm just summarize, right? You take the data you have, you smooth and interpolate it, so you put a curve through it. From that curve, you calculate this plot here. You plot incidence as a function of the cumulative number of cases. You replace that by an inverted parabola, and then you simulate or you solve the differential equation for the inverted parabola. It gives you this, which you can then compare to the actual data. And so here the dashed line is the estimated, what the model predicts, and the dots is what actually occurred. And you see that when you compare the two, well, they're not exactly the same, but they're not that bad. So in terms of getting an idea of what's going on, especially in an outbreak, you can use this. And so this is, so I'm going to show you other examples, right? So this is for the Dominican Republic, chikungunya again, so same story. And this is a summary of our predictions. So essentially what you have here, you have predictions that were made 1, 2, 3, and 4 weeks ahead of time, and they're compared to the actual values. The red line would mean that you get a perfect prediction. So this is in log scale, right? So obviously it's sort of compressing errors, but nevertheless, you see that, roughly speaking, you get the right order of magnitude. And I have two plots here. So this is one plot with only one parabola. And then this one is an example where in a situation where we use two parabolas. So then after we realized that it was working so well, because initially, so they didn't tell you anything about the competition, right? So we did this and we submitted data. I was just doing this out of curiosity, to be honest, to see how well it would work. And then like 2 weeks before the end of the contest, they wrote and they said, well, you're number 2, right? So then we had to write a report to explain everything, and then at the end we were number 1. So we were quite amazed by the simplicity of the model. And what we did is that we asked, well, does this work for other diseases? And so this is an example of an epidemic of gastroenteritis in a small nursing home in Mallorca. And again, you can see that you get the blue curve is what you get from the data, and then the red dash line, that's the parabola. So again, there's a good match between the two, and if you compare the predictions, you're almost right on top. This is Ebola in Guinea, and so it's much noisier, right? But again, you can sort of draw a curve like this through the data, and you see that when you run the model, it's not that bad at all. Right? So those huge fluctuations, they're sort of smoothed out. Like something like this, for instance, would be a huge error, but on average, you're picking up the trends very well. This is Ebola again in Liberia. So same story again. There are discrepancies, but it's not too bad. And then I have the one in Sierra Leone. So again, you smooth out huge fluctuations and you pick up the main trend. That's an example where you can put two parabolas. So there's one here and then another one there. And again, this is the comparison between the actual data. And then here you can make a prediction. The order of magnitude of the prediction that comes out of this is very good. It's exactly almost what happened at least as far as we can tell, the final count for the disease. And that's pertussis. And what's interesting is that people get vaccinated for this. So even if you have like vaccination, you can still pick up some information. So then we ask ourselves, well, why is it working so well? And one of the basic models for epidemiology is what is called the SIR model. So you follow the number of susceptible individuals, number of infected for I, and then the number of recovered individuals. So they either recovered or they died, depending on the severity of the disease. And so typically what this says, it says when a person who is infected gets in contact with someone who's susceptible, there's a likelihood that the person who was susceptible is going to become infected. So they move out of the susceptible pool and they get into the infected pool. And then people recover at a rate gamma here, and they move out of the infected and they go into the recovered pool. So it's very simple, right? And there are two parameters. Beta is the contact rate of the disease. It essentially measures how likely it is when you get in contact with a person who's infected that you're going to be infected yourself. And then gamma is the recovery rate. There's one parameter that everyone looks at in epidemiology. That's the ratio of beta to gamma, and that's called the basic reproductive ratio. In that case, this is for a disease that goes very fast, so you can assume the total population is constant. So N here, which is the sum of S plus I plus R, is constant. And to go back to the model that we were talking about, if this is a disease, the cumulative number of cases that I was looking at before is going to be the sum of those who have recovered, former cases, plus I, the ones who are the new cases. So I plus R is C, in my previous picture. So then you can take that and run, it's 3 ODEs, it's easy to solve. You can run the SIR model and then ask, well, do I see anything that looks like a parabola? So what I have here for two different values of R naught, so this is the time course of each component, right? So S is here, the infected people goes up and down, and then the recovered goes like this, right? So in that case, not all of the population was infected. But if you plot incidence as a function of the total number of cases, this is the blue curve. You see that in the SIR model, it looks exactly like something that looks very close to a parabola. And I plotted here two approximations, one which is something you can try to derive from the model, and the other one that's P2. And then P1 is the one you get from the data. If you try to match this the blue inverted parabola to a red one, the red one is the best estimate. And then for diseases that spread very fast, same story, you get an inverted parabola. So the idea essentially is that even in something like SIR, this inverted parabola thing is hidden behind the model. Now, because of this, you can create a small tool that people can use. So you can put again, the red is the parabola, the blue is the data, and you have sliders here, and you can try to change the sliders, so to switch the position of the maximum of the parabola or the value of C naught here, and in order to match as well as you can the blue curve. And we also have a sort of optimization procedure that does this automatically for you. And so if you start from here and you click that button here, optimize, this is what it tells you. This is for H1N1 in Canada. And that would be like the best parabola that fits the blue curve, essentially. And so we did some comparison with this automated method. I mean, obviously, it's not as good as what a human would do. But this is to give you an idea of what it does when you have intermediate data. So here, for instance, it's at the very beginning of the epidemic. If you try to fit a parabola through that blue curve, the automated method would just do this. But if you look at it and you know as an epidemiologist that the disease is just starting and that there's no way you reach the total number of cases, you can say, well, I want to put a parabola that does this. And then the model will tell you what the predictions are. And so as time goes on, as you get more and more information, you get a better approximation of the parabola. And so that shows you as the number of cases, as the epidemic follow its course, you get a better and better approximation with the parabola. This is just a table to illustrate we used 9 diseases and tried to make predictions on when the peak of the disease would occur, what the duration of the disease would be, and then the total number of cases would be. And this is described as a function of the percentage of the final number of cases that had been reported. So at the very beginning, you get a very large error, but as time goes on, the error decreases. But one thing I want to point out is that even at 30% here, the error is big, but it's not like 0.01, right? So the order of magnitude, especially in the number of cases, is reasonable. So if the model says, okay, maybe you have 10,000 people who are going to be sick, well, you can say, well, it's going to be 10,000, 20,000 maybe, but it's not going to be 100,000, right? That's the message you get from here. So to summarize, right, the new idea is to, which is very simple, is to plot incidence as a function of the cumulative number of cases and try to fit this to a parabola. And what this tells you is that the logistic equation is hidden behind the complex transmission models. Now, you can use this to forecast the magnitude of outbreaks, and it will work also for vector-borne diseases, right? So that's the connection with number one. If you know that you have any mosquitoes, because chikungunya is a disease that's carried by mosquitoes, it worked well. And the reason is, or at least an analogy, is that if you have a disease like the flu, right, and you want to model that with a mathematical model, you're not going to say, I'm going to model the molecules of air that transport the flu, right? And so here, the same idea, if you have lots of mosquitoes who are infected and things like this, you're not necessarily going to need to model the mosquitoes in order to get an idea of what the disease is going to do. And EpiGrowth, that's a little tool I showed you, that's an interactive tool that you can use to make prediction as time goes on. So right now it's in the form of a MATLAB applet, but we're hoping to maybe make an app with it so that people can use it. So my last piece is about transmission. So this is still preliminary, but I want to give you an idea of why we think it's interesting. And it's going to be about chikungunya and Zika in the small island of Dominica. So there was an article in Science back in 2013 that said that they look at pandemics. So they looked at SARS, I believe, and maybe H1N1 or something like this. And so it typically, like for SARS, you knew where it started from, and then you could see where it arrived as a function of time throughout the world. And the message of that paper is that if instead of looking at just geographic distance, you replace this by a distance that takes into account how many people move from one place to the other, then you can, instead of having something which looks random, then you can see a uniform propagation at a constant speed of the disease. Okay? So given this, I was curious to know whether or not this could be scaled down to something which is like local, right? So instead of looking at the whole world here, we want to look at a small country, and in that case, Dominica, because we had data for Dominica. So the answer that we believe is true, and again, I repeat, this is preliminary, is that yes, you can do this. You can do this, but there are two things you need to worry about. Is one, that you could have multiple points of origin instead of just one. And the reason is if two different people from, say, Dominica fly to a place where there is chikungunya, they come back home, they're not necessarily going to come back home in the same city. They're going to come back wherever their home is. So that would explain that you might have multiple points of origin of the disease within a given country. And the other piece is that you need to measure people flow. So here, for a pandemic like that, people were looking at airline data. So how many people are moving, are taking the plane and transporting the disease by air, essentially. But here, on an island, people don't fly. So for Dominica, the appropriate mode of transportation is by road. But the idea is that you need to sort of scale this approach down to and use a network that is the relevant transportation network. So I'm going to show you a little bit more of the details. So this is the island of Dominica. It has 10 major cities that are numbered 1 through 10. Roseau is the biggest city. It has at least like 10 times or maybe more as many people who live there than in the other cities. And then this is the road network. So they're not, I mean, these are the major roads, right? So there are not too many roads, but that's, so our colleagues from geography just, can collect this information very fast, right? which is very nice. So they provided all the information about the city location and the roads. And then we have two diseases here. So we have the location and the time of occurrence from colleagues in the Ministry of Health of Dominica, the time of occurrence of two diseases. One is chikungunya. These are the green dots, and then Zika, which are the red triangles. And so what our colleagues in geography can do, they have, like, if a disease occurs here, I mean, maybe just by looking at it, you can say, okay, well, it has to be associated to Roseau, but maybe there might be others, like maybe one here. You could ask, well, should I put it here or should I associate it with that? And they are like what they call the Riley law of markets that sort of look at how that distributes location, that associates location with big cities. So essentially what we did is that we looked at all of those cases and we associated each of them to one of the 10 cities. And there were only 2 cases that we could not allocate, but they occurred a little later, so it was not that essential. But so then you need to know how many people go from one place to the other, and you cannot put a sensor on the road, right, to sort of measure how many cars go by. So essentially we used another model that people use in geography, which is called the gravity law. So the idea is that the number of people that go from city I to city J is going to be proportional to the product of the populations of each city divided by a power of the geographic distance between those cities. So why is that? Well, because if you have a lot of people in city I, then you have more people who are likely to go to city J, so that explains the proportionality with PI. If you have a lot of people in city J, then the city must be big and kind of attractive, and so again that increases the likelihood of having people moving from I to J. Then you divide by the distance, because if 2 cities are very far apart, you're less inclined to go there. And the power beta here is sort of describing how difficult it is to go to that city. So if you have like a road which is badly maintained, you may not take the trip as often than if you have a very nice road. Right? So that parameter is essentially describing this. So you can, so what I'm going to show you is with beta equals 0.45. Then you do this renormalization trick. So you look at the fraction of people who travel to city J, how many are coming from city I. That's your Fij. You define a renormalized distance between city I and J as 1 minus the log of that. And then you calculate the minimum path on the network with those renormalized distances between any 2 cities. So, for instance, if I go back to the map, right? I mean, say I'm here and I want to go there. I would have to do something like this and that, right? Or maybe something like that and go here. Or I could also imagine doing this and then coming back somehow. But so you have more than one path to go from I to J, right? And then you look at the minimum, the one that's the shortest. And so now what I can do is put a plot here where I put this effective distance. So remember, this is not geographic distance, this is renormalized distance. And then here on the vertical axis is the time it took for the disease to go from the point of origin to wherever the city that's numbered here. So for chikungunya, which is at the top, we had 2 points of origin, city 7 and city 10. And then on the path of city 7, if you want, so we have cities 2 and 6. So that means that it took about like 40 days maybe to go from city 7 to city 2, right? And then it took much longer to go, from like about 80 days for chikungunya to arrive from city 7 to city 6. And then for city 10 as the point of origin, you get all of the other cities. And essentially what's amazing is that all of this go through a straight line. And what this is saying is that essentially you have a constant speed of propagation of the disease on that network. And so with the same network, we did that again for Zika, and you get a straight line as well, different points of origin, but the speed is different. So essentially now you have a method that uses the information of how people move to describe the speed at which the disease might spread. So you can measure, if you have information about the disease, you can measure that. But what's nice is that the network, the transportation network, the distances, once you calculate them, they're the same. Because it doesn't, the speed changes, so the speed reflects the nature of the disease, but the network is just the transportation, the way people move. So it has nothing to do with the disease itself. And so the idea is that once you have that, well, if I know exactly how many people move on that network, I can create, instead of having a map by geographic distance, I can have a map by this sort of renormalized distance. And it will tell you which cities are close to each other and which cities are far away from each other. And so once you know that, if say you have an outbreak in one of the clusters, then you know exactly where to look for the disease to go, and then maybe you can take some sort of intervention to slow this down, or bring hospital beds or whatever you might need over there, more doctors or something like that. The other thing is that once you have the rate of speed of the speed of each disease, you can try to connect it to the properties of the disease itself, the epidemiology part. And we found that so I want to get this right. I think I forgot now which one is faster, but Zika was faster than chikungunya, or the other way around. But this is not totally intuitive, but this is what happened in Dominica, and you can ask, well, why is that? Okay, so to summarize this piece, so essentially, in order to apply this method, what you need to know is how many people move from origin to destination for all of the possible cities that you have. And in order to calculate the speed, you will need to have some information about the time of arrival of the disease in various places. But the two things are essentially independent. You can still create the network without doing this. Now, I used the gravity law, right, which is something that geographers use a lot. But we have a little group of students here who are looking into trying to validate the gravity law. And so far we have results for the movement on the road network in the US, so in Arizona and the western US, essentially. We also have another group of students who are looking at transportation by boat in the Caribbean. And the goal here is to be able to describe the spread of chikungunya, or at least test if we can renormalize the distances in the Caribbean due to transportation by boat, if it turned out that chikungunya spread at a constant speed as well, using that boat network. And obviously it's not easy to get information about all of the boats that connect various cities in the Caribbean, so that's taking a lot of time. We're trying to also use the air transportation data in the Americas. Typically, this is almost impossible to find. You have to buy it. So we might do that. And we want to do this first and then see what this does. And essentially, as I said, the goal is to try to understand the spread of chikungunya, to see if this model applies to the spread of chikungunya in the Caribbean. We are, of course, looking on additional data for various diseases. So if you have such data, please, and you're willing to share it, please let me know. So I'm getting to the end here of the presentation. So I want to summarize everything we talked about and then see how we can put all of those pieces together. So I started with the mosquito model, and essentially that gives you mosquito abundance predictions, and the input is only how many, the temperature data, right? Temperature, precipitation, relative humidity. So climate data goes into the model. Once it's well calibrated, you can use it as a proxy for abundance. If you want to know exactly how many you can find in the traps, you will need some experimental data to compare it to. So you're going to, essentially, if you don't have data, you can just say, well, it's above average or below average by that much, right? But and the other piece is that you may want to recalibrate this locally, just because it's possible that the mosquitoes adapt to various locations. So it's very useful before you use the model to sort of get some sort of information for the area in order to calibrate it. But once you have this, you can describe risk, right? Risk of vector-borne disease, because it tells you how many mosquitoes you have. EpiGo, the little tool with the inverted parabola, you can use it to forecast trends once you know you have a disease that starts. And the network model is going to describe once the disease starts in one place, like an island or something, it can tell you which other places that are the most at risk to be infected first, right? So the idea is that you can put all of those things together if you have an outbreak. I'm not advocating for to model the flu or anything like this, but if you have an outbreak and you need to do something fast, this can work, right? Because all of these pieces go very fast. And so our immediate goals right now is that we were trying to build a transportation network model for the Caribbean. Once we have that network, we want to analyze the spread of the 2014-15 chikungunya epidemic there. In the future, we'd like to extend this approach to the rest of the Americas, right? So that's much. I mean, the Caribbean, you can imagine you go by boat, but once you get to Venezuela, or if you want to go to the other countries, you're going to need to take into account flights and other modes of transportation. And our next test is to look at Zika in Brazil. We found a paper that has very detailed data of Zika in the state of Bahia, and we have the road network there, so we're going to see if we can apply the method with more than one point of origin to that state. And as I said before, if you have epidemiologic data that you would like to share, please let me know. So before I conclude, I'd like to mention all of my collaborators. So this is like a little transdisciplinary team. We have, at the University of Arizona, we have people in the College of Public Health. Heidi Brown is an associate professor, an assistant professor, she's my colleague there. And then Riley and Erin are two undergraduate students. The School of Geography, we have Dao Chin Tong, she's an associate professor. Wang Xiu Mu is her graduate student, working with us on that. And then in the Department of Mathematics, which is my department, Kyle and Craig are undergraduates. Craig is going to continue on as a graduate student. Kyle is graduating with double major in math and computer science, and he's going to take a year off before he decides what he wants to do. Our colleague in Puerto Rico at the CDC is Roberto Barrera. He's the one who provided all of the data, the mosquito traps, and the weather stations. And in Dominica, we work with a group of people in the Ministry of Health and Environment who were able to share the data with us. And Charlottine and Ferdinia, Paul, and Sylvester Sanville. We got a little bit of funding from NIH and the University of Arizona. Well, thank you very much for your attention. You mean the second?
To predict a mosquito population, which equations did you use?
Oh, so there's no really, not really an equation. So this is an agent-based model. So essentially what we have is that each, you can think of a collection like a giant vector or collection of rows, and then each row corresponds to one mosquito. And so we seed it as an egg, right? And then it goes through all of those stages based on how the temperature and things like this. And it may not at any point in time, so we go day by day, right? So at any point in time, it can just die, right? And so you have this, we have like, the simulations I've shown you, they are about, on average, there's more than 10,000 female mosquitoes in those things. So it's a giant computer model. That's why it's agent-based in the sense that you're following each individual, right? And the advantage of this, I mean, that's the way the model was to start with, right? So that's what we've been using. But the advantage of this is that it's not hard to add an X and Y and Z coordinates. So you could also think of a spatially distributed agent-based model. Now, it's quite possible that I haven't done this, but I think that would make an interesting mathematics project, is to find macroscopic equations for the abundance. So essentially you could have a sort of a differential equation with stochastic input corresponds to the data that follows the mean, and then 2 for like the variance, and then essentially you would have your distribution bracketed between those two, for instance. And so people have done this for the SIR with stochastic input, but we haven't done this for this model. Yeah.
¿Alguna pregunta? excuse me, have you seen the opposite effect that in your graph, depending on the conditions of the roads or what you put, the conditions of the transportation, have you seen that if the epidemic stops at a certain connections and it doesn't advance anymore?
You mean use the network to, well, the idea is that that here, right? So the idea is that eventually it will people are moving around. I mean, especially here, right? I guess if you go to a place where no one comes out of there, but it could come from another path, right?
Yes.
So if the disease itself gets to a dead end, there might, maybe it's not going to leave that place, but there might be another way to go to other cities.
Yes, that's what I was wondering. If in your model, this effect of stopping is kind of impossible because what you were showing is that the velocity is kind of constant. So you don't have any idea if under certain conditions of the surrounding roads, it could stop like a front stopping at a certain level.
So I think that, for instance, you could say that. So if you renormalize the distances, right? So maybe here, this is a dead end, right? There's no way for people don't go from here to anywhere to there, for instance, right? You can say, okay, there's no nice way from this city to that city, but there is a way through here and then back down or something like that, right? So the idea is that this constant speed is not telling you where the disease is exactly, but it's telling you how likely it is that it will arrive in a given place at a given time. Okay, and because you have so many people moving around, then what's remarkable, I mean, it's not perfect, but what's remarkable is that you see this alignment. So that, roughly speaking, on that renormalized network, it's moving at a constant speed. But essentially, this is saying the disease is going to go everywhere, right?
And do you know how good it would compare if, in a larger scale, if you compare this model of the network with a continuous model? Because there are some models, for example, for the West Nile virus, of a traveling wave going from the east to the west in the United States. And there was some estimation of the velocity of the front.
Yeah, but I don't think they use geographic distance or something like this, right?
Yes. So I was wondering if in a larger scale, they can. There is a certain comparison between the model of the network and the continuous model. How do they compare?
Well, I think that. So, I mean, what matters here is that it be on this this renormalized distance network. Mm-hmm. Because if you were to put geographic distance here, instead of having a line, you would get a bunch of points that are,
Sure. But you can transfer back to the actual distance.
You can transfer
once
it back.
You plot everything.
That's right, but it's not going to look linear when you look in the actual distances. It's going to look weird, right? It's only when you look at it in this form that you would see the linear relationship. Now, what is true is that you can still ask, can I put a front on that network? And I think the answer is yes. I mean, for instance, what you can do is have an SIR model where you have in each city you have their own SIR, right? And then the people who are S or I, they move around and they can transmit the disease. So we ran that and we compared it. So you can, because with the SIR model you can choose your point of origin, you can do whatever you want. Right, so we used the network in Dominica. We put an SIR model on each of the cities. And we run that, and you get again a straight line, right? But again, only in that representation.
Yeah. Also about that, the same picture. So these are the points are the disease, like the peak of the epidemic in its area, in its city, or is it the start, or is the time scale much faster? Because supposedly there's also a time scale for the logistic map on each site or something like that.
Yes, so this is the time it took between the time the disease was reported at the point of origin and the time it was reported at the destination. So it's
So
not
the first incident.
First instance,
Okay.
not taking it. I mean, at least based on the data we had,
Mhm.
it's not taking into account the peak of the disease or
Okay.
anything like
How would the picture look if you took into account, or is there some?
I don't know. We don't have the data for that because we got like the first 500 and 800 cases of chikungunya and 800 cases of Zika, and I haven't tried, to be honest. We could do that on the SIR model, for instance, but we haven't tried.
But do you think that if you isolate its location, you would get again some kind of logistic like?
So in each city, you
Yeah.
mean?
Or
Yeah, I mean, so
in some bigger population. I mean, what is the?
So that's to connect back to the second model.
Yeah.
Right? And well, I think that if the city is somewhat isolated, maybe, but if there is a lot of mixing, probably not. So for like the countries in the Caribbean, obviously you could apply this logistic model to almost every single country. That's what we did, right? I mean, obviously for some of them you had to do two peaks instead of one. And we don't have a good reason for why that might have happened. We tried to, with all sorts of, access to healthcare, economic status, socioeconomic status, whatever. We didn't find any correlation. The only possible thing was a geographic, like if you have an island that's, with a mountain range in between, then you can get two things. But so I don't think, unless the disease spreads really fast in a given location. So I think it's a question of time scales, right? If the disease stays in a given city for essentially most of the outbreak, then I would believe the logistic equation would work. But now, if it starts, you can have input from a lot of places, and that is affecting the number of cases, and then I'm less certain. But we haven't tried.
Thank you.
Okay, so I would like to ask a question myself. So just to wrap up and to, I don't know, for the sake of the students maybe, could you please elaborate a bit on how you won this competition by proposing a simple model and incorporating data into it? So for students that are interested in modeling, how, I don't know, a take-home message for them would be what?
Well, so first of all, when I wondered what I was going to do about, once we had decided we were going to try to do the competition, and to say, what are we going to do about it? And if you think of modeling a disease like chikungunya, you can say, well, okay, I'm going to need, at the very least, an SIR model. Then I'm going to need a model for the mosquitoes. Then I'm going to need a model that describes how people move from one place to the next, so that I can describe how chikungunya is going to go from Saint Martin to Guadeloupe and other places. Right? And this very quickly is quite overwhelming because we don't have any of those parameters. So you can create a model, but then you don't know what to do with it. Right? So my approach in that case was to say, okay, well, I don't know what to do, but I know dynamical systems. And when you do dynamical systems, you have typically dx by dt equals f of x. Right? So x in that case was the total number of cases. Dx was by dt was incidence. So what I did, I took the data and I said, well, what is dx by dt? What is f of x? And once that plot came out, I realized, well, maybe we can just say it's a parabola, and that's not something that's coming out of any reasonable model that I knew at the time, because typically when you learn the logistic equation in a differential equation course, everyone tells you it's a toy model, right? It's something that you just do because you want to look at, it's simple, it's non-linear, but you can solve it. Whereas here, it's the data that said you can replace this by parabola. So the data was telling you, well, use the logistic equation. And once we did all this, and you go back to the SIR, this sort of inverted, upside down curve here, the blue curve, is not exactly a parabola, but it's close enough to a parabola to give you good results. So again, if you have the data, you don't need to know all of the parameters of the model. You can just build your model around the data. That's very different from what we normally teach when we do modeling and we do equations, right? We say, well, we want to justify all of the terms and then test all the parameters. But if you don't have the parameters, maybe you have a perfect model, but you cannot use it. So instead, you can use the data. That's the message.
Ok, entonces agradecemos a la profesora Jocelyn una vez más.
Thank you very much.